Okay, good morning, good afternoon, good evening, everyone. Welcome to our series on thermodynamics. I hope you're all doing great. So today we're going to continue from where we stopped last time in lecture 2 in the series Engineering Thermodynamics Made Easy. Now, let's share the screen. Last time, we spent a lot of time answering the question of what work is in thermodynamics mathematically. Of course, we know that thermodynamics is the study of the relationship between heat and work, how heat can be used to produce work, where work is mechanical motion, and then the flip side of it is how work can be used to move heat from a region of lower temperature to a region of higher temperature. Now, the first application where you generate work or mechanical motion through heat is applied in what we call heat engines, or generally engines. While the second part of it, which is upgrading of heat or moving of heat with work from a lower temperature to higher temperature, is what we find in refrigerators, air conditioners, and heat pumps. But we are going to be continuing with heat engines. And the question we answered last time was, what is work in thermodynamics mathematically? And we're able to show that each of these answers are in fact correct. Work can be described as force times distance for a constant force. At constant pressure, work done is pressure times volume. And this is a more practical definition compared to this, because we say that work is done in thermodynamics by the controlled expansion of a gas, where gas could be an air-fuel mixture. And expansion simply means a change in volume. And so, since gases have volume and they have pressure, then this equation comes in more practical than just force times distance, which is more practical in the field of engineering mechanics, where we're concerned about movement of points as against movements in volumes, as we see in gases. Then we also were able to show that torque times angular displacement is also a correct definition for work when we are concerned with rotational motion for a constant torque. And then we're able to also show through various graphical means that the integral of any of the first variables over the second variable is actually the general definition of work. So whether force is constant, pressure is constant, torque is constant, or even if they are not constant, the general expression for work done is the integral of the first variable, in this case force, over the second variable, in this case distance, in this case pressure over volume, and in this case torque over angular displacement. So putting all these together, we see that these four definitions are actually correct. And so the answer becomes option E. Now, by way of a recap into all these graphs the graphs that we use look like. Let's take the case of force against distance, a plot of a force against distance to illustrate the concept of work in general. We say that work in general is the area under the graph. Force, distance graph, pressure, volume graph, torque, angular displacement graph. The area under it is the work done. And work done is in general given by this integral. The integral of the first variable over the second variable based on the previous slide. Now, in this case where we're using force, linear force, and distance, then work is actually the integral from 0 to x, where x is distance, f of x dx, where f is force that varies with distance. So it's a varying force. Now, if you use what they call the trapezoidal rule, that is, if you discretize, if you cut this total area into small parts, and then you calculate the area under each small segment, and you add them up, it becomes a work done. Now, for a specific case, for the particular case where F is constant, as we showed last time, by the laws of integration, you will bring F out. So W will be F integral dx. And integral of dx from 0 to x gives you x minus 0. And so F times bracket x minus 0 is Fx. So for a constant force, we're able to show that W is equal to Fx. And as we say that the work in general is area under the graph. Now, what is the area under this constant force graph? Well, it is simply the area of a rectangle of height F and base X. And we know the formula for area of a rectangle, isn't it? Base times height, F times X. And that totally agrees with the equation we derived from the laws of integration. So you see the equation we derived from the laws of integration corresponds to the equation we derived from the area described under this line for a constant force. So now we've looked at different equations describing work done. Integral of F dx, integral of t d theta in the case of angular motion, integral of obvious one, integral of pressure against volume. So these are different definitions of work done. Now, when you are sizing an engine, the power, you talk about the power because the power is the key performance indicator. Power is like the rate at which it can do the work. While work depends on the time for which the engine is running. So a performance parameter of an engine cannot be work, but power, because work, basically the work done depends on how long for which you are using the power, for which you are operating the equipment, for which you are running the engine. So it depends on the user. However, the performance indicator of the equipment in question, the heat engine in question, is power. And so power becomes a very critical design variable or operational variable, heat engine. So how do we get power from work? Well, we have already given the definition. That is the rate at which work is done. So power is equal to dW over dt, that change in work over change in time. So if you are going from point zero, it becomes work divided by time. And so if we substitute work as f dx, if work is fx, dw is f dx, so we have f dx over dt. And we know that dx over dt, which is the change in distance over change in time, is what we call velocity. So power is also given by the expression force times velocity. V here is the linear velocity. Now, if you replace the W instead of Fx, if you make it PV, then you have power is equal to the pressure of the gas times volume over time. And volume over time is what we call volumetric flow rate Q, with SI units meter cubed per second. And so if we go into the rotational motion domain, then dW is T d theta, because we say that work done for a constant torque is the torque times the theta, which is angular displacement. Isn't it? From our previous videos, you will see that work is the torque times angular displacement for a rotating system. And so, angular displacement divided by time is angular velocity. Just like linear displacement divided by time is linear velocity. Angular velocity divided by time is, angular displacement divided by time is angular velocity. So power can be given as torque. That's angular velocity. So this is a very popular equation for power for an engine. The mechanical power delivered is simply a product or the product of its torque and its angular speed. Now, this angular speed in radians per second can be related to revolutions per minute. And we will show that in one of our subsequent lectures. Okay, so let's try and let's now state some of the fundamental laws of thermodynamics. So the first one we're going to state, which is very important, is the first law of thermodynamics. So what's the first law of thermodynamics? Simple. It's also called the law of conservation of energy. It says energy can neither be created nor destroyed, but can be transformed from one form to the other. I believe that's self-explanatory, isn't it? So energy does not just come from nowhere, and it cannot be destroyed, but it can be converted from one form to the other. So put in another way, we can call it energy balances, that energy, the total energy in a system is always balanced. All the energies coming into a system equals all the energy going out of the system. So if we look at a heat engine, this is a classical diagrammatic representation of a heat engine. It takes heat from a high temperature source does work with it, and then releases residual heat to a low temperature sink. So if QH is the heat it receives from the hot temperature reservoir or from the high temperature reservoir, and then work, W is the work done by the heat engine on its surroundings, and QC is the heat rejected by the heat engine to its surroundings. Then the sum total of all the energies going into the heat engine is equal to the sum total of all the energies flowing out of the heat engine. So if we follow the direction, we'll see that QH is equal to W plus QC. That's the first law of thermodynamics for a heat engine. Simple and straightforward, isn't it? Then we can now subsequently maybe do more calculations on what happens here, probably what happens here, and what happens here from where it gets its heat energy. But this is the fundamental statement of the first law of thermodynamics governing the operation of a heat engine in relation to its environment. When we talk about the environment, we're talking about the source, the sink, and the equipment it is driving. For instance, driving a vehicle, driving a generator, and so on. Driving a train, driving an airplane, driving a car, driving an electric generator. So, okay. Now, let's look again at the first law of thermodynamics. Let's go beyond the heat engine and let's look at it from a general standpoint. Now, from a general standpoint, the principle remains the same. Energy cannot be created or destroyed, but can be changed from one form to the other. Now, this statement reads thus: the heat added to any system equals the work done by the system on its surroundings plus the change in its internal energy. That is, energy is not created. Energy is not destroyed, but it can be converted from heat into other forms of energy. And the sum total of the other forms of energy will be equal to the heat added. And now, from the point of view of the thermodynamic engineer, there are essentially only three forms of energy. Form number one, heat. That's why we say thermodynamics. Thermo is heat, dynamic is work, and then we have the others. And the others are classified under the general term internal energy. Internal energy. It could be chemical energy, it could be other forms of energy, but they're all classified under the term internal energy. So now let's look at what happens here. Here we see a boiling pot, water in a pot boiling. Now at the beginning, we had cold water in the pot. When you apply heat to that cold water, initially, there's no mechanical motion of the water. Rather, the temperature of the water starts rising. That's change in internal energy. So the heat, all of the heat added is converted to a change in internal energy, which manifests as a change in temperature. There's no work done at that stage until when it gets to boiling point. When it gets to boiling point, then ebullition occurs. Boiling occurs, as you see, there's mechanical movement. And so if you have a lead, the lead will be displaced up and down, up and down. That's work done. So at that point, the heat added is equal to the sum of the work done plus or and the change in internal energy. In fact, at that point, at the point of boiling, you might see that the temperature does not change. And so change in internal energy will tend to zero, while all the energy you supply will convert into work. Displacement of liquid water and then generation of steam. So steam will start escaping. So in a sense, it's a kind of expansion of gas, isn't it? Because the steam will start expanding, displacing and leaving the system. So that's mechanical motion. And so assuming the system is confined, it is covered such that there's no way for the steam to escape. And at the same time, it is movable like a piston. Then the steam will actually displace in a controlled manner the lead up from its initial position to a position or positions further down or further up in space. So you see that basically the first law of thermodynamics tells us the relationship between heat, work, and the other forms of energy, which we classify as internal energy. And a change in internal energy, in this case, manifests in a change in temperature. So that's a statement of the first law of thermodynamics. Now let us make a statement of the second law of thermodynamics. Now the second law of thermodynamics can be stated in various ways. So this is one of the statements which is called the Kelvin-Planck statement, which says that it is not possible to have a process whose sole result is the absorption of heat from a reservoir and the conversion of this heat into work. So we cannot have this kind of process in the real world. We cannot have a heat engine that converts all the heat it receives into work. A residual heat must be discharged to the low temperature environment, to the sink. It has to be, because if not, then we'll say the heat engine is 100% efficient. And we know that in practice, in real life, a heat engine cannot be 100% efficient. So this second law of thermodynamics sets the stage for the definition of a key performance indicator of a heat engine, which we call efficiency. Efficiency is a rate or is a ratio of the work done by the heat engine to the heat received from the hot reservoir. So if this process is possible, that means efficiency will be 100% because all of the heat is converted to work without a residual heat rejection. This violates the second law of thermodynamics. Second law of thermodynamics, in a nutshell, in terms of the Kelvin-Planck statement, states that the efficiency of a heat engine cannot be up to 100%. There are other statements of the second law of thermodynamics, especially those relating to entropy irreversibilities and things like that. And we're going to look at them later, and we're going to show why, based on those, why the efficiency of a heat engine can never be up to 100%. So we're going to solve some example numerical or calculation problems. It's a relatively simple one, isn't it? An engine absorbs 10 kilojoules of heat from a hot reservoir, rejecting 7 kilojoules per cycle. Calculate A, the efficiency, B, the useful work done per cycle. I believe you can do that. Do it, get your answer, put your answer in the comment section, share the video, like the video. In case you've not subscribed, please do subscribe and help our channel. Thank you. So we go ahead. Here is basically a solution to the problem. So an engine absorbs 10 kilojoules of heat from a hot reservoir, rejecting 7 kilojoules per cycle. So if we look at the block diagram representation of the system, we see that QH is the energy absorbed from the hot reservoir. So that's the 10 kilojoules. QC is the energy rejected to the cold reservoir, which is 7 kilojoules. And by the law, first law of thermodynamics, all the energy coming in, QH, equal to all the energy going out, W plus QC. So if you do a change of subject of the formula, you see that W, when QC goes this way, it becomes QH minus QC. So W equal QH minus QC. And so if QH is 10 and QC is 7, then W will simply be 10 minus 7. That's 3 kilojoules. That's the second one. While the efficiency, which is QH over, which is W over QH, by the time you manipulate this, W over QH will essentially becomes 1 minus QC over QH. And so you substitute and you get this result. So in a nutshell, the efficiency is 0.3 or 30%, while the work done is 3 kilojoules. Okay, let's do another example. In this diagram, you see a power plant, basically, a steam power plant. The steam could have been generated from gas, from some other source of primary energy. So the steam turbine is coupled to the shaft of a generator. And by the time the steam turbine rotates, the shaft of the generator rotates with it. And of course, EMF is induced in this coil and power generated. So in a power plant, high temperature, high pressure steam with an enthalpy of 500 megajoules is supplied to a steam turbine like this, which converts this thermal energy into 200 megajoules of mechanical work. This mechanical work in turn drives an electrical generator to produce 180 megajoules electrical energy. Calculate one, the energy dissipated at heat from the turbine low pressure steam, the turbine efficiency, the generator efficiency, the overall system efficiency, and the overall system efficiency if the steam turbine is driven by a gas boiler at 85% efficiency. Can you do that? I trust you can do that, not so So try it out. When we come next time, we continue from here. All right. So today we've been able to expound further on work, how work is done, and we'll be able to do some few, just one, easy calculation problem in thermodynamics using the first law of thermodynamics. We will to introduce the first law of thermodynamics as the law of conservation of energy, that energy can neither be created nor destroyed, but can be converted from one form to the other. And we'll be able to show that to the thermodynamic engineer, there are essentially three forms of energy: heat, work, and the others. The others are classified under the general term internal energy. And that when heat is added to any system, that heat leads to two effects. One, work. Two, change in internal energy. And when no work is done, then all the heat is converted to a change in internal energy. And when there's no change in internal energy, all the heat supply is converted to work. So in general, heat supply Q is equal to work done W plus change in internal energy delta U. That is another way of stating the first law of thermodynamics. And we're able to show what that means, particularly using a boiling pot example. And we also showed a statement of the second law of thermodynamics, a statement known as the Kelvin-Planck statement of the second law of thermodynamics, which states that it's not possible to convert all the heat received by a heat engine to work. There has to be some losses. I believe it's all clear. If there's anything that's not so clear to you, write on the comment section. I'll reply you. So till we come your way again, same time, next time. Thank you for listening. Thanks for coming. Please do keep coming back. I appreciate you. Like the video, comment on the video, subscribe in case you've not, and share the video as widely as possible. Thank you.